One last subject just to finish up our discussion of ketones and aldehydes and some of the additions that they do is the subject of alpha-beta unsaturated ketones and aldehydes. These are going to pretty much appear as note card reactions, but we're also going to talk a little bit about mechanism just because some of the mechanistic steps and moieties that we'll be seeing are something that's going to apply to enolate chemistry when we finally get to third term. So, an alpha-beta unsaturated system, as you might expect, let's just do an example of one of these things because it's probably the most common example, is anytime you have a carbonyl group that on the alpha and beta positions down here, which I guess I can label pretty easily, obviously these systems have like an unsaturated double bond there. And so what we can remember from any time we have the potential for a resonance hybrid, even if it's really ugly, is that we have a little bit of double bond character of this, what looks like just a normal old single bond. In other words, we've got kind of a communicative system of p orbitals that those electrons can all kind of flow along. So, this system, it's really nice to have a set of reagents to do two different things. One is to build new carbon-carbon bonds, and the other is to reduce really specific parts of these things. Of course, we could beat the heck out of it. We could do some sort of reaction that we have to purify, but let's come up with some really nice reagents that'll do some really specific things for us. So, the first thing that we're going to talk about is how to reduce, because this is not the most difficult thing in the universe. It turns out that if we want to just reduce this double bond, we are just going to employ our normal friend H2 with some sort of fancy transition metal, right? As long as we're careful with this, right, and we just kind of use normal bomb flasks, I know that sounds kind of funny to say, just a normal bomb, the ketone group is going to be unaffected by these reagents. And so what we would expect is just specifically reducing that double bond and leaving that carbonyl oxygen alone. Of course, as we got more and more aggressive with this type of reaction, we will eventually start to turn that thing into an alcohol. But that's something that requires a lot of extra work. In fact, these reagents that we discovered do reductions really well, which are those hydride reagents, were really discovered as kind of originally people trying to kind of lower the necessary conditions, extreme conditions of doing that kind of reduction, right? So what we've learned already, I just want to make sure that you recognize that this possibility exists, is that if we're going to use some sort of hydride reagent, our old friend lithium aluminum hydride, sodium borohydride would also work here. It turns out that we can selectively reduce this to the alcohol and leave that double bond alone. So it turns out that there's all kinds of really useful syntheses that can involve these types of reductions. And of course, six-membered rings are a really important moiety in all kinds of synthetic problems. So now let's take a look at ways that we can make new carbon-carbon bonds in alpha-beta unsaturated systems. So to make new carbon-carbon bonds, we're going to employ two old friends. One is the Grignard reagent, and the other one is that thing that we called the Gilman reagent. And if you remembered when I was discussing some of these things, usually the Grignard reagent is kind of like the hardcore, like they actually call it the harder of the two. In terms of reactivity, and so you'll see how that translates here. And then the Gilman reagent always does something kind of similar to the Grignard, but often is a little bit more gentle with its approach. And these things are called soft nucleophiles, which is actually a word I hate, but I'll use it anyway. So anyway, let's say that we want to create a new bond with a Grignard. And so we'll just kind of let's pick out, oh, I don't know, phenyl magnesium bromide or something like that, right? Right? So we are always going to do a quench step after that. Keep in mind that when we see a Grignard, that MgBr, really that's saying that we've got like a carbanion on that aromatic carbon. And we've seen the mechanism of this before. It's just going to be a simple addition to, a simple basic addition to that carbonyl group. And so what we'd end up with is a brand new carbon bond, just as we would have expected, and a tertiary alcohol. And let's just put a pH there for the phenyl group because I'm running out of room. Right? So that's not surprising. Well, take a look at what the Grignard reagent does in this case. And let's say we've also got some sort of aromatic moiety that we'd like to employ here. Right? There's my Grignard reagent, and just for fun, let's finish it with a quench. It turns out that when you treat the Grignard reagent with an unsaturated system, where you put the bond is very different than with the Grignard, right? You'll notice that the phenyl group now added to the beta position, right? And so this type of alpha-beta unsaturated system is going to have all kinds of important consequences in third term. We're going to see the fact that that beta carbon is really special in terms of its ability to react with a certain set of soft nucleophiles. Like, for instance, a nitrile group would do the same kind of thing. But this is the first example of what we've seen, or what we're going to see here. And I just wanted to kind of go through a little bit of this mechanism, pretty simple, so that we can kind of see where this thing actually came from. So let's write down this guy as the carbanion form. Of course, there's a lot more complicated stuff going on with what this copper and lithium are doing in the actual reactive species. So we'll kind of simplify it just a little bit. And what we're going to see is that this carbanion can attack that beta carbon. And we're going to have a flow of arrows that looks like this. And one of the reasons I kind of I like to end this subject with this intermediate is that it is what's called an enolate, right? And we've seen this before. These enolates are always in some sort of, well, almost always in some sort of tautomerization reaction, or kind of a more specific way of saying an isomerization reaction, where the second that we treat this thing with any kind of acid, we're going to be able to move electrons like this. And you'll notice that when we get through that strategy, we get to the ketone, right? And so anytime you see an enol or an enolate, especially in third term, we know that there is a ketone very close. Right? So that's something that I definitely wanted you to see. We'll just kind of leave this here. We're trying to kind of keep, pretty low key this week. And so, add this to your stack of note cards, and I think it'll help you out.